Now, we would like to invite Zainab bin Aziza, Secretary of IEEE RAS ENICarthage Student Branch Chapter, to share a few words.
Assalamu alaikum, everyone, and welcome. I hope you are doing well. Since we have some new participants joining us today, I would like to take a moment to briefly introduce our chapter so you can get to know us better. IEEE ERAS ENICarthage Student Chapter is a dynamic community dedicated to robotics and automation. Our mission is to inspire and support students through hands-on projects, technical workshops, and collaborative learning. We aim to create an environment where everyone can learn, innovate, and grow together while preparing for real-world engineering challenges. I hope you will enjoy today's session, and please don't hesitate to ask questions during or at the end of the session. I'm confident that our trainer will be happy to answer all of them.
Thank you, Zainab, for your insightful words. In an era of rapid technological evolution, this five-session program offers a progressive, hands-on journey through robotics from the fundamentals to advanced concepts, exploring robotic architecture, embedded systems, and real-world applications in a format that's kept simple, interactive, and accessible to all experienced fields. We are incredibly honored to have Mr. Ihab Marzuki joining us on our virtual stage today. Mr. Ihab Marzuki is a mechatronics engineering student at the National Engineering School of Carthage, ENICarthage, and the chair of IEEE Aerospace and Electronic Systems Society chapter, ENICarthage student branch. Today, our speaker will guide us through the fundamentals of embedded hardware and interfacing, exploring the differences between microcontrollers and single board computers such as the STM32, ESP32, Arduino, and Raspberry Pi. The session will also cover essential communication protocols, including UART, I2C, and SPI, demonstrate how sensors and actuators are integrated through GPIO configuration and hardware interfacing, and conclude with a live hands-on demonstration of connecting a sensor and reading real-time data. Everyone, please give a warm virtual round of applause.
You for your presentation, and it's honor to me so much. So, assalamu alaikum, everyone, another time. Thank you for joining this session. My name is Ihab Marzuki, third year mechatronics engineering student at the National Engineering School of Carthage, former chair of IEEE ESS in Carthage SBC, and I am your training for this wonderful session, inshallah. Thank you again for participating in this session, which is one of choosing between collaboration between IEEE RAS Unica Student Branch Chapter and the IEEE RAS NCU Student Chapter. Okay, just 1 minute. I will share my presentation. Everyone, do you see my presentation? Good.
Yes, it's visible.
Okay. Just 1 minute. Let's present. So as we said today we'll introduce the embedded hardware and interfacing, moving from the comparisons between microcontrollers and the single board computers, understand how both talk to each others, and to sensor to via many types of communication protocols like UART, I2C, SPI, and we will finally with real life robotic application. Here, welcome everyone. Let's start our presentation. Here's what we'll cover today. First, microcontrollers, this single port computers. This gives us the foundation. Then the communication protocols, where we'll look at UART, I2C, and SPI, and how ports actually exchange data. After that, sensor and actor interfacing, then the GPU configuration and hardware integration. We will also close with a hands-on demonstration where we connect and read the data from real sensor, live and sound commands to real actor motors. First, the microcontrollers. Okay, here we in this words we have a lot of type of controllers. But let's start with building blocks. Microcontrollers is a single board computer. This is are two main types of brain you will see in almost any robotics and or embedded projects. We have microcontrollers and we have single board computers. You see, the microcontrollers is a single chip that integrate CPU, RAM, and flash memory. Of course, the CPU is the processor of the single card, the RAM, where our program the program will execute. When you type a program in microcontroller, it's executed in the RAM, and of course the flash memory. The memory will where your program is stored, and the peripheral like GPU. GPU is means the global purpose input output, timers, ADC, and the communication interfaces. The microcontrollers are they have no operating system by default. You write bare metal code and you run lightweight RTOS like FreeRTOS or Zephyr. It's deterministic. You can know exactly how many cycle until it's your all of code executed. So actually, it's depend on your application. If you want to know how many cycle your code takes to execute all of code, you can know it. It's very simple. Just you have to know your clock. For example, the STM, its clock is 168 megahertz. Then by some equation, mathematics equation, you can know how many codes will take times line by line. Of course, each line have some characteristic. For example, when you define a variable, it's take one cycle. When you make a condition, it's take, for example, two cycle, and then you can know exactly how many times you can your code can take to execute all. Another advantage of microcontrollers, it's low power cheap, low power, it's cheap and boot instantly. Doesn't takes time to boot. We have here a lot of types of microcontrollers, like as you see in the pictures, Arduino Uno. Also, the Arduino have a lots of types like Arduino Uno, Arduino Nano, and many other Arduino Mini. Also, it's small and smaller, cheaper. We have also the ASP32. Even the ASP that also have a lot of types, ASP32 and ESP32 Mini, and the Xilinx card. And finally, we have the most card that used in robotic and automation robotics, which is STM32. Until now, everything is clear. Thank you. Moving now to the single board computer. The single board computer, or the SBC, is a full computer on a small board. It usually has a multi-core CPU, RAM, storage, and it's run a full operating system. The operating system that we usually use is Linux because it's open source, and it's very helpful and for robotics application. It can make multitask, run multiprocessor, and has networking stack, file system, and can run Pythons, OpenCV, ROS, and out of the box. Of course, who knows the ROS? The ROS is one of the most framework that they used in robotics and autonomous robotics. So it's need to computer to OS to run ROS because he run multiple nodes in the same time, and that's cannot be run with microcontroller. That's why we need to use single board computer like the Raspberry Pi or the Jetson Nano. Another characteristic of the single board computers, it's not deterministic by default. The OS scheduler decide what runs. A real-time task can get delayed by other process, and of course, and another disadvantage, it's high power draw, slow boot. Sometimes the Raspberry Pi takes 1 to 2 minutes to boot, and the Jetson Nano can take more than 2 and 3 minutes to boot also. Let's take now type per type for the microcontrollers, starting with the Arduino Uno. Arduino boards like the Uno are also MCU-based simpler chip, like it's used the 80 mega 3028 MCU. It's big and friendly ecosystem and a huge library collection and a simple idea. Actually, it's the best for prototyping, teaching, simple project where raw performance doesn't matter. Robotics use its quick proof of concept before graduating to STM32 production design. So as I said, Arduino Uno is the simplest microcontroller card that you can learn from it, the basics of embedded system. You can make a lot of prototypes with it. It's very ecosystem and beginner friendly cards. Also, the software engineer develop a lot of library, so it can help you for a lot of application by the Arduino IDE interface. Moving now to the ESP32. The ESP32 use the Tensilica Extensa LX6 core, but its key feature inbuilt Wi-Fi and Bluetooth that makes it ideal for wireless sensor nodes and remote telemetry. In robotics, you will see ESP32 used for things like wireless kill switch, remote telemetry, dashboard, or distributed sensor nodes on a swarm of robots. So the advantage of SP32 uh, and compare with the Arduino, it's integrated with the Bluetooth and Wi-Fi module, so you can use it, and you don't need an extra module to plug it in. And of course, it's very useful cards for IoT application, and when you need to send data via wireless like Bluetooth and Wi-Fi. Also, it's data of communication and data of execution. It's more powerful than the Arduino also. And moving now to the best one for robotic application, which is the SEM32. The SEM32 use the RAM, ERM Cortex M family running bare metal or Anertos real-time operating system. It's best known for practice precise timing, PWM generation. Here we talk about motors and encoder reading and the closed loop control plus low power consumption, and the most advantage it's high pins count and the bigger variant. So as you see here, STM32 has much pins compared with the ESP and Arduino, which has lower number of pins. As you see here, there is a lot and a lot of pins. It actually has up to seven ports from E to F, right? The STM32 development tools. Here I have taken a picture from the real data sheet of this for the STM32. I choose the type of discovery because, of course, even the STM has a lot and a lot and a lot of types. And in starting project robotics, the types of STM32 discovery, it's very good and very helpful. So I choose it and to for this for the session. So as you see here, this architecture of the STM32 discovery. Here you can find the her CPU and the Ethernet USB, DMI, it's direct memory access. And here you can find the GPU A, B, C, D, E, F, and Intel I. And it's handled with a lot and a lot of feature like timers. Here you are communication, we will see before this step. I2C communication can, and a lot of peripheral we can use it, much more other devices. As you see here, there is a lot and a lot of timers, but the ASP32 and the Arduino have only two or three timers. So in comparison with the STM and other boards, as microcontrollers is the best one. So that's why it's very useful, and we need this card for autonomous robot. It's so helpful. You can use the STM. You can use it. Its MCU by direct addressing data sheet, and you can read its data sheet, and you can address directly to each register, and you can read sensors from each pin as input and make output as for actors like motors or I don't know some things. So you can make this directly or using the HAL, which is a hardware abstraction layer. Explaining easily, the HAL is very is library that make the development easier by providing high-level functions instead of direct register manipulation. So here's robotic software developers are developed the HAL, which is hardware abstraction layer, to make it easy for us to manipulate the codes in the STM architecture because it's very complicated. As you see, it's not like other boards. That's why, and we will see an example for the HAL. Moving now to the Raspberry Pi. Raspberry Pi is the best for anything that needs. Yes, Muhammad Aziz.
Ihab, can you go a little bit slower so our
Okay,
members can understand?
okay, thank you so much. Sorry, there was the velocity. Sorry so much. Okay, the Raspberry Pi. The Raspberry Pi is best for anything that need a full OS. Full OS, which means like Linux, Windows. That's full OS. Also, camera processing. You can use it for ROS nodes running neural networks. Also, you can run on it computer vision AI models. It support them because it's, as I said, it can process a lot of nodes simultaneously, like, and it can run a lot of topics and nodes. And networking and web dashboard also, it's very good for these applications. In robot, the Raspberry Pi usually act as the brain. For example, when we want to build a robot, the Raspberry Pi is the brain of the robot because when we want to make autonomous robot and want him to act autonomously, Then we have to use the Raspberry Pi and other cards for commands, motors, and other sensors. Until now, it's clear. And if anyone have a question, stop me, and I will explain every bounds. So now it's good. Everyone who heard me. Okay, thank you, Alish. The Raspberry Pi setup tools. Actually, the Raspberry Pi, if you want to configure it, you have to processing these tools, starting with the Raspberry Pi imager. It's software application. Here you can find the OS of your Raspberry Pi. For example, if I have a Raspberry Pi 5, I will enter to this software and I will choose Raspberry Pi 5. Then I will flash its OS and the SD card. Then I will put the SD card in the Raspberry Pi. Of course, I will with another setups like the storage, the customization, the wire, the writing, and the and you're done the flashing. Unreal VNC viewer to remotely access to the Pi desktop without needing monitor flagging. So as I said, after flashing the image of the Raspberry Pi in the SD card and put the SD card in the Raspberry Pi, you can access to its image using this application, Real VNC Viewer. We will take a real example at the end of the session. We'll show you how this goes. And here's a composition table between all boards we talked about. The STM32 that use core ARM Cortex-M, the SP32 use Xtensa, and the Arduino use Atmega 3028. And the Raspberry Pi, of course, use ARM Cortex-A, it's multi-core. The clock here, you see the most highest one is the STM32 is up to 4018 megahertz. The OS is, of course, the microcontrollers haven't no OS, they are bare metals, and the Raspberry Pi they adapt with the Linux OS. Real-time capability for the STM and the SP32 and Arduino are good, but for the Raspberry Pi are poor because, as I said, it's take a lot of time to boot, and it's much better to work with it when with another functions. It's better for navigation, notes like vision notes, leaders notes, and other application, and for real-time capability like launching motors, active motors, read sensors. It's helpful to use STM32 or ESP32 or Arduino. For wireless, the STM32, only the ASP and the Raspberry Pi has built with Wi-Fi and Bluetooth. And as I said, the typical robots, here are some example for typical robotics roles. Until now, it's okay. Thank you, Arij, again. Thank you, Ahmed. Now let's move into the communication protocols, UART, I2C, and SPI. Let's start, of course, with the types of communication before. In communication, we have three types of communication: the simplex, half duplex, and full duplex. The simplex before the simplex means data flow only one direction. The receiver can't replay. Think of traditional radio broadcast or a keyboard sending input to a monitor. The hard duplex means both sides can send and receive, but they have to take a turn, like a walkie-talkie, where you press push to talk and release to listen. A full duplex means both sides can send and receive at the same time. Highlight these words at the same time with no waiting like a phone call or a modern network connection. So this is small explaining about those typing. It's necessary to know the types of communication. Until now, it's okay. Understood, everyone? Do you what? What is UART? UART it stands for Universal Asynchronous Receiver and Transmitter. It's a protocol for exchanging serial data between two devices using just two wires, TX and RX. Of course, TX is wired to RX and RX is wired to TX for the other device, as you see here, the wiring. For example, this is the first device, and this is the other device. The TX of the first device, it should wire it to the RX of the second device, and the RX of the first device should be wired to TX of the second device, and it should have the common GND to ensure the stability of the communication. Uh, okay. By the way, your word can be simplex, half duplex, or full duplex, depending on how you use it. But it most robotic setup, you will use it as a full duplex with data flowing both ways at once. Okay, understood? Moving now to the frame structure of your UART. Here's the frame structure of the data that sent and received from the UART. So here the data start with start byte logic to 0, and there is and send eight other bytes from 0 to 7. Those are the word data, and here's a parity byte. This byte it's for CPU to understand that the data is changed or not, because sometimes cause to the temperature or some issues, the data can be changed. So this parity bit it's for knows that the data is sent clear with no noise, and the final bit is a bit of stored data. So when two devices are connected to each others, this is the data. This is the type of data starting with start bit data, the word. This is the data, and then this is parity data to avoid the noise. And finally, it's completed with stop byte data. And here, critical things to have to take in mind. No shared clocks. Both sides must agree on bound rates in advance. For example, the Arduino, it use 9,600 byte per second, and the SP make the other two device in the same bound. For example, when you are connecting two cards, for example, let's say USB32 and STM32, the both should be agree in the same baud rate. For example, as I said, this baud rate or this baud rate. Okay, understood. Okay, thank you so much, Said. Moving now to the I2C. I2C is a synchronous protocol using the master-slave architecture over just two wires, the SDA and for data, and the SCL for clock. Multiple devices can share the same two wires because each one has a unique address. So as I said here, the I2C protocols, it's very simple. Data for a wire or a pin for data, and another pin for a clock. So under this communication protocols, you can make a lot of devices in the same line, because in the microcontroller each device have a unique address, so they can communicate all of those devices in just two lines. For example, you can make a LDC here and MPU and another controller. For example, this is Arduino Uno and this is Arduino Nano, and this is another devices is sensors of gas. So you can wire all of them in two wires, and based on their address, you can each time select each one from each one you will receive or send a data. It's clear. Here's the frame structure of the I2C, as you see here. The overview of I2C frame. It will start by byte also. The data, the slave address, as I said, if you have a lot of address, here you can find your slave address, your device address, and here you will this byte for read or write. For example, write is 0 and read it's 1, and act byte, and this part is for data, and act also, and final byte it's for stop byte. IDC is widely used for protocol for exchanging data over short distance, two wires, as I said, SDA and SCL, a master size control of the bus, and then read of wires of frame containing slave address and one or more bytes of data. Moving now to the third type of communication protocols, which is the SPI. Its definition, it's a synchronous serial communication protocol. Also, it's based on master-slave architecture. If you see here the SPI and I2C, both of them, they use the master-slave architecture, but the UART node is point-to-point, and it's clock provided by the master who send the clocks, and the simultaneous full duplex communication selection via chip select. I'll explain it. For example, here we have a master board. Let's say the master here STM32 or ASP, and here's some slaves, like here we can say this is a sensor 1, sensor 2, sensor 3, even you can say sensor 1, sensor 2, and another board, Arduino Nano, for example. So here's the master can be wired to all of those devices in the same wiring, but as I said, everyone have a unique address, so it can access to him via its unique address and via chip select. So its characteristic, it's a synchronous serial, because synchronous it's use the clock. Mode it's full duplex, mother slave. It speeds up to more than 50 megahertz. Here's its pins: the MOSI, the master out slave in, out slave in, and the MISO, master in slave out, the serial clock, and the slave select or chip select. So here, if we want to wire a master with slaves, it's very simple. It's wiring our MOSI pins of master to MOSI pins of slaves. For example, MOSI here is wired to MOSI slave 1, it's wired to MOSI slave 2, and it's wired to the MOSI of slave 3. The same for MISO and clock, and here shape select or slave selects, select 1, select 2, select 3, to everyone, to every time select 1 to accept for him. Is it understood?
Yes.
Yes.
Okay, thank you so much. So this is the communication protocol, the architecture of the data. Here's the clock from the controller, and this is the data. It sent from the master to from the master to the slave, and also the slave can send the data from the slave to the master. The type of this is data is sensible to raising edge. Do you understand what does raising edge mean? Raising edge is when the front go from 0 to 1. It means that name it raising edge. And when the edge it's down from 1 to 0, that's falling edge. Here it's sensible to raising edge. Also, this characteristic it's can be manipulated via the code. You can choose in which type of edge your control is sensible. Okay. And here's some conversation table between all of communication protocols, the UART, the I2C, and the SPI. For wireless, the UART it's need two. It needs two wires, TX and RX, and one GND for communication stability. Also for I2C, SDI, and SCL, and one GND for common GND for stability also. And for the SPI, as we show later, they need four pins and one common GND. It's a speed. The reward is low mid range. It's up to 1 megabytes. But the I2C it can up to 100 kilohertz and 4 megahertz. The SPI, the highest speed, it's 100 of megahertz. Topology, it's point to point, multi-slave address and multi-slave and CS selected. Full duplex, the URTS, it can be full duplex. The I2C, no, it cannot be full duplex. But the SPI, yes, it can be full duplex. Typical robotics use, as I said, UART can be a board-to-board communication, for example, PI and STM32. We will make a real example after the presentation. And the I2C also it can be board-to-board. Also, it can be board to sensor like AMU, PME 280. And the SPI, it's high speed sensor, so it's basically used for the SD cards and displays. For example, when the protocol communication between the SD card in the Raspberry Pi and the Raspberry Pi, it's SPI because, as of course, it's should be read and write the data very highly. Okay. So thank you for your attendance, and now we'll move to show you real real examples. Just 1 minute. So here, as you see, I will open the camera too. This is a small ESP32. It's linked with MPU 1615 sensor. So via the your I2C communication, I read the data and I display it in the serial monitor as you see here, data of acceleration and rotation and the temperature too. I will show you how things. Some minutes. So I will show you how I make this small example. So as you see here, the board of ESP32. I have two pins that can make the communication I2C, which is this one is GPU 22 and GPU 21, as you see here. So that's what I make exactly. I wired this two pins to the MPU, and then I make a small code to read the real data from it, as I showed to Arduino IDE. And now I will move to another example. Just 1 minute. I will show you another communication between Raspberry Pi and the STM32 via UART communication. I will show how to access to the Raspberry Pi. It's really simple command. First, after making, I'll show you. After making the power and plug the power on the Raspberry Pi, it's lighting here, so it's working. I will accede to her using its idea. This is the command to access to your Raspberry Pi. You have to first connect to it via the PowerShell using SSH and the PI, and then PI address. This is the address of PI, but I have some technical problem. Just 1 second. I'll fix the technical problem. I'll return 2 minutes. Share the Raspberry Pi image. This is the image of the Pi. I will go to my workspace. Then the project autonomous robot. Now we'll open the camera. See the robot. Okay. Do you see the robot clearly?
Yes.
Okay. So there's what we have exactly. We have the communication between this single board computer, which is the Raspberry Pi 5, and the STM32 is the microcontroller. The STM, like you see here, it's discovery types. So what type of communication exactly? What the Raspberry Pi will send to STM? It will send a command to run the motor. After make some vision node and resolution. Here's we make the communication, the wiring between them. We wire two pins TX and RX to the STM and the RX to TX. Also, and one common GND between them, and then we'll run. Second. I will first make the authority of PI to use. Sorry, just 1 second. So as you see, sorry, it's the robot, and here as you see in the camera, after making the permission of the Raspberry Pi to use the communication of UART, then I will launch a Python script. I will explain what this script do exactly. Okay, it's launched. So as you see here, you will read this. See this. Just 1 minute. Now, look. This camera vision For robot autonomous, here it will detect the load and will send the command to the STM. As you see the commands here, this is the commands set by the STM, and then the STM will turn the motors. And here we can, this is a small project of autonomous robot, as you see. Just 1 minute. Okay. So this is everything for today's sessions. I hope you enjoyed the session, and now I'm open for your questions. Everyone, if you have any questions about the smaller projects and the architectures or the protocols communication, I'm pleased to answer you. And this is my contact information. If you want another information, I will be so pleased to help you with another thing. Everyone, no one has a question?
Thank you so much, Mr. Ihab Marzuki. We are now opening the floor for a brief question and answer session. So if anyone has any questions for our speaker, uh, please feel free to use the raise hand feature, or you could simply type your questions as well in the chat and just relay your questions to us.
So I think everything is clear. Thank you again for the invitation. I'm very honored to be with you today to make this wonderful session. Thank you for your presence. I hope you enjoyed the session. Thank you again. I hope to see you again another project and another event.
Yes, before we end this session at this stage,
Okay.
I would like to call Zainab bin Aziza, the Secretary of IEEE RAS ENICarthage Student Branch Chapter, and Shamsia Monira, the Vice Chair of IEEE NSU Robotics and Automation Society Student Branch Chapter, to present a token of appreciation to our respected speaker on behalf of IEEE RAS ENICarthage SPC and IEEE NSU RAS SBC.
I just want to thank Mr. Ihab Marzuki for his time and dedication. It was a great presentation and we really appreciate all the effort he put into making the session so informative. I would like to thank all of you joining us today. I hope the session was beneficial for everyone and that you found it informative and valuable. We look forward to seeing you again in our upcoming sessions. Thank you all and have a wonderful day. Assalamu alaikum.
Thank you everyone for joining, and especially to our speaker for giving us such an amazing session. We really look forward to having many sessions in the future as well with you guys. And we have a small token of appreciation for you to show our gratitude and your contribution in this session. Thank you so much. And now I think are we guys ready to take a screenshot?